Thank you very much. So today I'm mainly going to talk about how to accelerate diffusion models. So first, I would like to talk about two observations during the diffusion denoising process. So it is two types of redundancy in diffusion models. We call it the spatial redundancy and the temporal redundancy. So for the spatial redundancy is, as you can see in the top row of the figure, is that tokens at the same time steps are highly similar to each other. For example, in the background, the white sheet shares many similar tokens. And the second type of redundancy is temporal redundancy, which is the tokens across adjacent time steps are highly similar to each other as well. For example, for the same background scene token, during different time steps, especially the adjacent time steps, they are pretty similar to each other. So this raises a simple question, is that how to accelerate through these diffusion redundancies. So we can mainly separate these acceleration methods into three types. So which is the temporal acceleration. What we try to do is we try to reduce the actually computed steps during the diffusion process. For example, we try to reduce a 15-step diffusion model into a 4-step or 8-step through distillation or maybe feature caching or even DPM solver. And the second line of work is that we can do spatial acceleration, which means we reduces the actual computation of each step. So this is totally orthogonal with the temporal acceleration. So we can use sparse attention or like token proning or token merging to do spatial acceleration to reduce each step's computation. And the third type of acceleration method is the model compression, like quantization, model distillation, and maybe proning. Yeah, but today we are mainly going to focus on the first two. So first of all, I would like to talk about the feature caching for temporal acceleration. So there's a former work called deep cache and fast forward cache. And they have a main observation is that they printed all of these attention similarities and MLP similarities of different models in DIT, of different layers in DIT. And they find out that the attention similarity and the MLP similarity in adjacent time steps are extremely high. Like, for example, the diagonal and its surrounding regions are pretty bright, which means the adjacent time steps shares a pretty high similarities. And also, while the layer goes deeper and deeper, the attention similarities and the MLP similarities are more and more obvious. So which means there's a lot of space to do acceleration and do compressions. So this results in two classical types of feature caching, which is feature reuse and feature forecast. So the fast forward cache first claim out the feature reuse pipeline, which is we do not compute the whole 15-step of the diffusion models. We compute several steps. And then after we computed these several steps, we cache all the layers, all the DIT layers output, and then we reuse it for the next n steps. Like, for example, if you want to achieve like a 3 times or a 4 times acceleration, you can just compute one step and then you reuse it 3 steps. You reuse it 4 steps, and then blah, blah, blah. So a recent work called Tyler further improved this method by replacing this simple reuse mechanism to forecasting by using Tyler formula. So basically is that instead of simply just reuse these cached features, we computed these computed these cached features as differences to approximate its derivative. And then with these derivatives, we can approximate the Tyler formula to predict the next feature so that we can predict the next feature without computing through the large diffusion network. So, however, most of these feature caching methods are implicitly assuming that all of the hidden dimensions in DITs involve under a single and unified system, so that they can apply a single and unified reuse or forecast mechanism to skip the computation. There is a classical observation in Tyler is that they do a PCA projections in DIT-XL2, and they find out the features in different time steps and the derivatives of these features in different time steps shows a pretty continuity, and it is easy to be differentiable. So as you can see in these two figures, the left figure is the features in different steps. As you can see, the trajectories are pretty continuous, and the derivatives of its trajectories are also continuous as well. So as a result, we can formulate these continuous feature trajectories so we can formulate these predicting these continuous trajectories into a sequence solving problems, like a time series solving problems. So, however, Taylor find these observations based on DIT-XL2, which is a relatively small models. The parameter size is less than 1 billion parameters. So, however, nowadays, the diffusion models scale up a lot. For example, the FLUX and the Qwen-Image all have like 20 billion parameters, and the hidden size, the hidden dimensions grows up as well. So this raises a central question to challenging its assumption, to challenge the previous assumption, is that does all hidden dimensions still evolve under a single and continuous system in today's modern diffusion transformers? So intuitively, feature space is pretty high dimensional, and it exhibits complicated behaviors. So such complexity is unlikely to be captured by a single and unified process. So we try to dig it further. We do feature space analysis on FLUX. Like first, we do clusterings. We try to find out how each feature dimensions changes over time steps, and we group them into clusters based on their dynamics. So basically, we group them based on like the first order differences, its second order differences, the curvature, and the jerk ratio, blah, blah, blah. And we find that the feature space should be better described as a complex systems, where different groups of dimensions follows distinct temporal patterns. For example, on the left figure, we can find that the trajectories in cluster 1, they are much more oscillatory. And the trajectories in cluster 2 becomes much more smooth and continuous. And we found this similar observation through frequency decompositions as well, whereas the low frequency part seems to be more unstable and the high frequency part seems to be much more continuous. So what we're trying to do is we utilize these analyses and we apply them during inference. So this is the classical HyCa framework, which is called the hybrid caching. It stands for the hybrid caching framework. So what we try to do is we first analyze each model's feature space through feature clustering, which is, for example, for these feature maps, we try to compute its indicators for temporal dynamics. As I said, there are several indicators such as first order differences, second order differences. These shows the trajectories geometry features. And then based on these geometry features, we try to cluster these trajectories into different groups. Like for example, the dimension 1 and dimension 4 seems to be monotonous. Like the color is getting brighter and brighter. So which means their trajectories share the same temporal dynamics. And then they will be grouped into cluster 1. They will be grouped into cluster 1. And the same as cluster 2 and cluster 3, blah, 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 with similar temporal dynamics. And then after we grouping them into different clusters, and then we try to find the best solver for each clusters with these optimization formula. So this basically means that for each cluster, we try to use the selected solver. We try to use our selected solvers. For example, there's like 10 solvers in our solver box, and we try to predict the next feature through our cached feature, and then we compare this cached feature. We compare this predicted feature to the actually computed DIT features, and then we compare its differences. So with the smaller differences means that the solver is more suitable for this cluster. And with the larger differences, which means the solver is not suitable for this cluster. And eventually we will assign the most suitable solver for each cluster. So after we save these solver selections and our cluster results, when we do an inference, we apply them. So for example, for dimensions in cluster 1, we will use the most suitable predictor. For example, the RK predictor. And for cluster 2, we will use the AM predictor, blah, blah, blah. And the pipeline is like, the feature prediction pipeline is like, we first compute 3 steps. For example, in this figure, we first computed 3 steps for historical as the historical feature, and then we apply its solver to predict the next 3 features, to predict the next 3 steps without computing the large DIT networks. And then we compute the DIT network again for an accurate feature, and then we apply the solver for the next 3 time steps, and blah blah blah, and goes on. So what we found interesting is that, so in the last PowerPoint, as you can see, if we want to do a fast inference, we cannot do this clustering and all of these analysis during the inference because it takes a lot of time. For example, k-means takes a lot of time to find out the best cluster. But what we found interesting is that we can actually do a one-time clustering and all-time solving because the cluster assignments and the solver selections are input invariant, which means they are invariant with the input prompt, the resolutions, and on different time steps. They are all pretty similar. So we do a adjusted rand index, and we try to compute the adjust rand index of these cluster assignments. And we found that most of them, they are above 0.8, which statistically means the 2 distributions are pretty similar to each other, are very similar to each other. And we found that when we do cluster assignments on different prompt, different time steps, or even different resolutions, the distribution and the cluster assignments are pretty similar to each other. This allows us to evaluate our solver performance on a single prompt at a single time steps to reliably identify the best solver and achieve results comparable to a large-scale training or a large-scale evaluation. So this observation is was found similarly on another CVPR paper, which they do SVD decompositions. And they find out they do SVD decompositions on feature space. And they find out the SVD matrix are highly similar and consistent as well. So for example, the 3 matrix in SVD, and they find out the last 2 matrix are extremely similar across prompts and resolutions. So based on these one-time clustering and all-time solving mechanism, we only need to do a simple offline study for each model, and then we can reuse these cached solver assignments and the cached clustering results during the whole inference pipeline without computing it again. So the offline costs are extremely small as well. For example, it only takes 1.1 second on FLUX to find out the best solver and the cluster assignments, and 4 seconds on HunyuanVideo. And all of these time are offline costs, so they do not appear during the inference. And as you can see, we use a simple demonstration of the cluster numbers. We set them as 2 for a single demonstration. And we find out no matter how the prompt and how the resolution and the time steps changed, the solver selection and the cluster results are extremely similar. So based on our hybrid cache framework, we achieved pretty well generalization on all different kinds of models. For example, on text to image generations, we can achieve like a 5.5 times acceleration, while still remaining extremely similar to the original pictures. And also we can do it on image editing as well. For example, this column is the original model's output, and this is our HyCa output. Yes, and we can accelerate it like 6 times with pretty similar outputs. And we also do it on text to video as well. So one interesting part is that normally when we are talking about feature caching, it is pretty hard for feature caching to adapt with distillation because they are both temporal accelerations. They all reduces the actually computed steps. For example, if you distill a 15-step model into a 4-step or 8-step model, it is pretty hard for feature caching methods to predict the features because the distillation makes the interstep differences become significantly large, and these causes traditional caching failed. But however, HyCa treats these distilled variants as new models and searches for the best solver as well, which can kind of alleviate the prediction errors to some extent, but not fully solved. We will talk about this question later. So we can also achieve like a 2 times acceleration even on the distilled model. So totally with like a 25 acceleration ratio. So although HyCa, I think it's a practical framework, but there are still pretty much limitations. For example, that HyCa does not fully address the intrinsic prediction errors in step distilled models. And also, our solver pool is just like a fixed linear combination of historical features, which constrains its flexibility. And also, HyCa needs to pretty extra memory consumptions. And more is that the speed up becomes marginal for extremely low step models such as 2 steps and 4 steps. So based on these limitations, we have some further works. So first is feature caching with distillation, as I just said. So it is pretty hard for traditional feature caching methods to adapt the huge interstep differences with the with step to distillation models. So what we are trying to do is we try to compress a large video model into a few step model. So this is pretty hard for both feature caching methods and distillation methods. So distillation maybe can compress the image generation into like a 1 step or even a 4 step, but it is pretty hard for large video models to compress smaller than 8 steps. So what we try to do is we try to prone a very popular distillation method called mean flow, and then we try to prone it into a restricted mean flow. So this can alleviate a bit of its prediction error, because if you want to do a 1-step generation on video model, this training target is pretty hard. So we reduced its training target into several steps, for example, like 4 steps or 8 steps first. And then we apply the feature caching methods to reduce these 4 steps or 8 steps to an actually computed 2 steps or 4 steps. So what we first do is we do a restricted mean flow. For example, the original mean flow tries to train the mean velocity of the whole generation process from the beginning to the end, which is from 0 to 1. And we try to degrade its training target to a relatively simple, which is we try to train, for example, the first 10 steps mean velocity, and then we train the next 10 steps mean velocity, and then blah, blah, blah. So we changed these 1-step generation methods to a few-step generation method. And then after turning these large video model into a few-step generation model, we try to train a small caching predictor. So instead of using these training free aware caching, we try to train a small predictor to predict the feature. because in distillation model, it is much more harder to predict the feature. So there are two losses we actually used for the training the predictor. The first is the classical MSE loss, which is try to find out the differences of the actually computed DIT trajectories and the predictor trajectories. And the second one is the GAN loss, which is we train a small discriminator to discriminate the predicted feature and the actually computed feature. And the second work based on HyCa is that we try to train a linear predictor for caching. Like as I mentioned, in HyCa, most of those solver sets are just linear combinations of the historical features. So what we try to do is, since we all use these linear combinations of the historical features, so why can we train a linear predictor? So a linear predictor can predict its features much more accurate than those fixed linear combinations. So this is the second work. And third one is how to alleviate and how to reduce the caching memories. So instead of caching all of the layers output, we try to cache just the last layer's output. And this reduces much like 90% memories. This reduces like 90% caching memories, which and also it introduced a minor quality degrade. So beyond these temporal accelerations, as I mentioned, so today's diffusion acceleration, I think it is more and more difficult to do spatial acceleration because it is pretty hard to reduce the actual computation or the actual computed tokens in every steps. And based on today's mainstream industrial acceleration is step distillation. So what we try to do is we try to do several spatial accelerations to mix up with distillations, and so that it can gain extra speedups even on distilled models. This is much more easier than you apply another kind of temporal acceleration methods with distillations. So first, I would like to talk about several previous spatial accelerations on other domains, for example, on VLMs and in LMs, for example, like token proning and token merging. So these traditional methods reduces the actual computed tokens during inference. So however, when applying them on diffusion models, they shows pretty much quality degrades. For example, on this figure, when we apply this token merging methods on diffusion models, and as you can see, the bird feather and the details degrade a lot, and it only achieves like a 1.25 times acceleration ratio. So this is a relatively low acceleration ratio with a high cost. So I think this is mainly because of the token merging and the token proning methods are breaking the original latent grid structure and the geometric information during the denoising process. For example, if you try to find out some tokens that are not be computed during the denoising process, these tokens are separated on the whole image. They might be here, they might be here, they might be here. And so the geometric informations of the original image is broken. So it is pretty hard for these methods to actually work on diffusion models. So what we try to do is, instead of we choose which tokens and or which token to merge, which token to prone, we just reduced the latent resolution during the denoising process. So actually, it's like we compress the whole image into a lower resolution. So what we call this is the progressive resolution sampling. We reduces the resolution at the beginning, and then we upsample it later in the denoising process for fine gain details. So this achieves like a substantial speed up on few steps models, and avoid the problems that I just taught. So because this during the whole progressive resolution sampling, the informations of the images are largely reserved because you just reduced the whole resolution of the image. And the geometric informations are reserved as well. And we find it have a pretty good performance on image generations and video generations. For example, it can achieve like even higher clip scores and semantic scores on even higher than the original model on video generations and image generations. And we found it pretty weird. So because normally when you apply acceleration methods, you can't achieve a better score than the original models. So this confuses a lot. And the other thing confused me a lot while doing this project is that previous dynamic resolution methods, they often follows a structure called the pyramid structure of denoising. So which is, there's a lot of paper observed this, and I'll just talk one of them, which is called the pyramid attention broadcast, is that they find that the attention differences during the diffusion steps shows different patterns. For example, during the first stage of the denoising process, probably from step 15 to step 13, and the attention changes a lot. But during the middle stage of the denoising process, the attentions barely change, and it changes a lot in the last stage of the denoising. So that this can be illustrated like the figure here. So basically, is from the noise to image. The first part of the denoising is like when the image is trying to build up some semantic informations, and then it's the bottleneck. The bottleneck is less important, and then the final stage of the denoising is important again because it needs to generate fine details for the image. And there are lots of progressive resolution methods follow these pyramid structures. So what they do is they do not compress the latent resolution at the first stage. They preserve it, and then while changing into the middle stage, they then compress it to a lower resolution, and then they upsample it again during the last stage for details. So they believe that if we preserve the full resolution in the beginning stage of the image generation, the semantics informations can be largely preserved. But this is there's a pretty big problem lies in this mechanism, is that when you're applying these methods to a few step generation model, there is no middle step. Like for a 4-step or 8-step models, if you try to preserve the full resolution, not only in the last stage, but also in the first stage, so the actually speed up you can gain is pretty small. So you can speed up a lot. So this seems to be a trade-off between speed or semantic informations. But what we found in our test is that even we started the image or video generation with a lower resolution, the semantic score are even growing higher than the original model. So this is pretty confused, and this confused me a lot. Until recently, I read a paper called Improving the Diffusibility of Autoencoders. So what this paper trying to do is they try to do regularization after the VAEs compressed the image or the video into latent. So they do regularizations to reduce the high frequency components of the latent space. And then they find out that after reduce these high frequency components, the model performance even better than the original VAEs. So this is pretty similar for our progressive resolution, because when you are doing downsampling at the first stage of the denoising, you're actually passing the image through a you're actually passing the image through a through a through a low pass filter. Yes, so you're actually reducing the high frequency components of the image as well. So I think this is part of the reason that why we can achieve even better semantic score than the original models and these bottleneck sampling methods. So also, we try to scale these dynamic resolution samplings into video generations as well. But video generation is a little bit different than image generations because it has a brand new dimension, which is the frame dimension. So the original image generation only has the height and the weight, and the height and the width. And now we have another temporal dimension, which is the frame. So this is a little bit more complex than singly compressing the resolution. Like in video generation, we can not only compress the resolution, we can also compress the frame rate. So what we found is that if we jointly compress both the resolution and the frame rate, it can achieve a much more better speed up gains and also preserves a much more better quality, because in with different video prompts and video content, they seems to show different dynamics. For example, there are some videos, for example, this guy is running. So this is like a motion scene, and there are some static scenes, for example, like this flower, they just stay the same for the whole video. And also there are many complex scenes with pretty much objects and human hand moves. So different videos requires different spatial and temporal compression strategies. What we're trying to do is we try to estimate the spatial and the temporal demands, and then we jointly compress them during the beginning stage of the denoising. So this is our framework. So first, we try to use the noisy latent to generate a sketch video latent, which is a few step sketch video latent. And then we use these sketch video latent to approximate how much spatial and temporal demand it needs. For example, for this image, it requires a larger spatial demand than its temporal demand. And then we try to find the best solver for this video. So we construct a candidate action set. So these action sets are several actions about how to compress the video, some with much more larger compression ratio on temporal. Some have a larger compression ratio on spatial. And then based on these spatial demands and temporal demands for each prompt, we try to find the best candidate action set for them. So for example, for this video, maybe it needs a balanced compression methods. And then during inference, after we generate the sketch video latent and then find out its best action set, we compress the video with a reduced resolution and then with a reduced frame rate. So after these generation, and then we scale them, we upsample it to the full resolution and the full frame rate for fine gain detail generations. And this achieves this becomes pretty successful when combining with distillation. For example, like as you can see, these are the figures generated with dynamic video generation and combining with mean flow. So this is like a 18 times speed up, but still remains highly similar to the original video. And this is another demonstration as well on HunyuanVideo 1.5. So it shows like a pretty good compatibility with CFG distillation and mean flow. And so after we compressed like an 18 times speed up, it still shares like the whole same content. And that's all. Thanks for listening.